Thanks. So hi, I'm Tom Scholl. I'm with NLayer. I'm no longer at the phone company. And and 9.5 years. So pretty much what this is all about, and it's an experiment that's been basically going on in my free time over at NLayer. And somebody actually reminded me last week when I did all the slides and I showed it to them, and they said, this has nothing to do with about actually building a cheaper pairing router. This is really about buying something cheap and just doing some tricks. And actually, yeah, that's true. So for anybody who was expecting, to get in the nitty-gritty of how to actually build a router, I'm sorry if I got your hopes up. So what's this really all about here? And basically, network infrastructure can be expensive. And that applies to different people, right? Certain really, really big companies are perfectly happy with buying really gold-plated interfaces, and their operating overhead is really probably more their issue when it comes to upgrading peering. But for a lot of other people, actually the routers and the optics and everything added up is a considerable amount of cost. And when it comes to upgrading peering infrastructure, there's a variety of issues that come into play. If you're not going to do it for your network, you have to do it for the person that you want to connect to. If there's no ports available, oh, I'm sorry, we'd like to upgrade, add another 10 gig. Sorry, there's no ports. We have to add another router, but hey, we can't get any more space. There's no power. And then the ports themselves have a cost associated. And depending on how you operate things, you look at a pairing port. Oh, well, it's not revenue generating. It's not a customer port. That's another issue too. And the other part too that comes into this is that 10 gigabit Ethernet is basically pretty much the standard lately for any kind of interconnection between networks. It's not, you still don't find a lot of N by gig bundled up. It's generally at that point people are doing 10 gig, N by 10 gig. And at the same time, a lot of different networks have basically decided to move away from big traditional SONET type boxes, GSR, CRS, Juniper T series, to really more boxes that are really Ethernet centric, have basically built for Ethernet. And but pairing routers still are a significant expense within their infrastructure. And the boxes that are currently out there in a lot of people's networks, they're running out of steam with regards to how many ports, density. You can only do 40 gig per slot on this box, and now you're just waiting for the newer cards whenever they get certified and they work with new code. So there's a lot of problems that come in play when you have to upgrade stuff. So vendors have kind of reacted to a lot of this Ethernet-centric kind of platforms, right? So historically, you had Cisco GSR, CRS, Juniper T series, big old metal style boxes, right? And then at the same time, you've had a lot of Cisco 6500 enterprise kind of focused box, which have been reinvented with a lot of new cards. That's pretty popular in a lot of content networks and all over really. And there's kind of this middle tier that kind of came out here of boxes with a lot of 10 gig. So Juniper MX, Cisco 7600 with some of the ES cards, the ASR 9K from Cisco, and Foundry MLX XMR. So that's nice, and they work, and the ports are fairly reasonable compared to what they used to be. But at the same time, there's also been a lot of other 10 gig boxes that have come on the market, right? And they're really targeted at the data center, top of rack role. They only do data center optics, particularly SFP+, nothing really long reach. They may be lacking in large packet buffers. A lot of the advanced features that you typically find on a service provider grade router, they don't have. And underneath the hood, it's really commodity merchant silicon running it. That may not be from that vendor themselves, right? And they have some other characteristics which are pretty neat as well. So they're small, 1U, 2U. It's meant to go top of rack, so they're really dense. They do have larger chassis type boxes, which are 16 to 32 type boxes for slots. And they're built on using SFP+, and it's cheaper optics, so it works pretty well. So some of these boxes you could say, well, the ASR 9K, it's based upon Easy Chip, Juniper EX is Marvel, Dell Force 10, Foundry, different boxes there. You'll see it's actually Brocade. Arista has Fulcrum chips underneath it. So kind of just playing around here. Well, could you actually take some of these cheaper boxes and actually put them in a kind of a service provider, internet type of role? Obviously vendors probably wouldn't like that. You're using a box that's meant for this other purpose. No, buy the bigger one. Well, there's some obvious, really glaring challenges to doing something like this. So, limited fib size, right? Internet's 330,000 prefixes. These boxes can only do maybe 8 to 12,000 prefixes that you can actually install. QoS, if that's something you need, well, they've got some limitations there. Decent software, well, we're all used to, a good CLI as pipe commands, things like that. You're probably not going to get all that. Packet filters, you still have to protect your border of your network, and some of them have limited functionality there. And in general, like the actual forwarding features themselves, MPLS, IPv6, a lot of them are starting out with just, IPv4 support, although that is obviously changing. And all these features, there's somewhat difficult for some of these smaller boxes to actually implement. So going off the first one, which is the fib constraint one, which is a pretty obvious one. You're putting this box in the pairing role. It needs to have lots of routes on it, lots of paths. You can't obviously install to the fib because the box can't handle it. So one idea here is, well, let's separate the rib versus the fib. So the rib holds all your routing protocol information, so your BGP routes, your IGP routes, and then the fib is what actually gets put in the forwarding plane. It's what's used for forwarding packets. Now, what you could do here, you need to have definitely a large rib because you're going to be pairing. You're going to get potentially multiple copies of the internet table, all your peer routes. So the rib needs to be fairly large. But since the rib is basically stored in memory, RAM is cheap, and a lot of the 1U2U boxes that are shipping, do come with like 1 gig of memory, so it's not typically that big of a problem. And this kind of goes to the key of, well, maybe you don't need to install every single route on whatever your cheap box may be. QoS, how many people really are actually in, when you're pushing internet bits, and that's your, your core business, how many people are really, flexing and using a lot of the QoS capabilities besides Anton Campella? So how many people really actually use it and play with every single feature in the network? A lot of networks that are just pushing internet bits, it's very common to find that QoS just isn't configured anywhere. Now, if you look at a lot of traditional, large telco style networks where they are doing multi-services, where they are transporting layer 2 VPN, layer 3 VPN, IP transit, they're building everything on a single network. And for them, yeah, QoS is probably important. And because everything's on one network, they have to guarantee that level of service for those customers paying for, pseudo wires and whatnot. But for anybody else that this isn't, really hard requirement, maybe lack of QoS isn't really a showstopper. The other part is lack of forwarding features. A lot of these boxes were designed for the data center. They're devoid of a lot of the features that you're going to find on a service provider type box, right? And a lot of the things that are pushing these, cloud computing and lots of servers in a rack. That's kind of driving things to go beyond just regular layer 2 networks, and you're seeing new protocols being put here. So trill, shortest path bridging, and in some cases even like VPLS on all these boxes as people move to using that within the data center in a more smaller environment. Are driving some of those features to be put in some of these boxes. And a lot of it's still on the roadmap, right? But it looks, there's still significant demand, and it's, it seems to be coming out fairly soon. The other problem is, you do need to have packet filters, right? You're on the internet, you have a router there, you have lots of routers internally, you need to protect your own infrastructure. So it's pretty reasonable to say you need to be able to put some sort of X amount of line ACL to at least stop packets coming in your network towards your point-to-points, towards your loopbacks. It's a pretty reasonable request. And at the same time, you still have, your customers calling up, expecting you to be the packet police and telling that, some IRC server is getting attacked and you have to filter it for them. So you have the one-off ACLs you may have to apply. At best, you could probably get, on some of these smaller boxes, you can, ACLs that'll go up to layer 3, layer 4, but that's typically about it. Don't expect to see anything like matching on packet length, policing even, or even matching on some exotic things such as, IP options or IP options type. You're probably not going to see that. And then you could also say, well, can you use null routes and things like that, and remote trigger black holing to protect the infrastructure? I mean, there's ways to get around, just relying on packet filters to protect your network. The other part is actually decent software. If you look at a lot of the cheaper 1U, 2U boxes, the software is not really all that great. And that's mainly because the people, producing the chips for them, this isn't their area, their specialty. And why should they? I mean, they're building chips. They don't really want to, rebuild iOS or Junos or anything like that and put in routing protocol stuff. Do you really want Intel to be writing your operating system? You don't want probably Broadcom to be writing your OS on your router. In some cases, a lot of the OSs that come are really slimmed down. So if you look at the Dell, the Force 10 S50, things like that, the CLI is pretty simple. It's basically turn up and down ports. Maybe you'll get SNMP, but it's very limited functionality. And in general, when they do try to release any kind of software, have like a third party create it, it's iOS-like because it's made for the enterprise, and certainly a lot of people there know how to do iOS, but it's iOS in like the worst possible way. It's a first grade level. You have show, you have config, maybe a few other things, but that's about it. A lot of other vendors who are producing these types of boxes, they'll pay a third party to actually write the software, but it's pretty much, just the bare minimum to get it out the door. And, they're not adding, they're not really basing the box on, feature parity with other devices on the market. And I'm not going to go into this too much, but there's another thing going on, which is OpenFlow, and there's a whole other series of talks at this NANOG covering OpenFlow, which it'd be best to defer to what they're talking about, and I think what they're doing in that space is pretty interesting, and I'm sure we'll hear a lot more on it. But I think it'll be open a lot of doors in terms of what you can do on some of the cheaper boxes out there. So what's unique about this approach? What are we getting at? Using this cheap box that's going to do routing. How does this even going to work? If you got a limited fib, and a lot of this comes up with basically kind of exploiting BGP unicast label. And at a previous NANOG, I think it was in Austin, we talked about doing some kind of routing tricks with building LSPs to external interfaces. And we kind of highlighted BGP unicast label. And you could use the same application here. And basically, BGP unicast label is another BGP address family. So you have IPv4 unicast, IPv6 unicast. There's a variety of other ones, but unicast label is an interesting one where it's basically you can advertise a prefix and associate an MPLS label with it over BGP. And that's kind of similar to how LDP and RSVP allocate labels, except they build the LSP end to end. In this case, you can just basically say, here's a prefix, here's a label, and that router makes a local allocation within it, saying for this prefix, here's the label that you'd use when you forward any traffic to it. So let's try a little experiment. Let's say if we were going to take one of these 1U2 type boxes. So we'll say Juniper EX4500. It's like line rate, 40 by 10 gig E, 2U, 8 to 12K fib, and 1 gig of memory. And the idea is let's take this box. We'll hang it off something smart, some sort of core router. And for our purposes, we'll say that core router probably has a full table on it. And we're just going to use this little cheap box, and we're going to basically either throw off customers or throw pairs onto it, something that it needs to talk BGP to. And you could debate on does it really need to hang off something smart or not. And a lot of the reasons why you'd want to hang it off something that has a full-size fib is because you're going to have to route to things back internally. There's ways you can kind of get around that by encapsulating traffic and sending it to another router. But for the purpose of this, we'll just hang it off something that's smart. The other part is you definitely want this cheap box, whatever it is going to be. It needs to establish IGP adjacencies. So it needs to be an active member. It needs to be able to learn how to recurse to loopbacks. And that's important for a few reasons. First of all, if you're going to bring up BGP sessions to something internally, you probably want to do that across your loopbacks and not actually with the actual point-to-point interfaces. The other part is, you're going to be advertising routes externally in your network. You need to make sure that if you're going to do something like you're going to take the IGP cost and push it into the MED when you advertise externally, you want to make sure that the IGP cost maybe is representative, the MED is representative of, the actual IGP distance within your network. So it pays to have that visibility. Other things too, such as next hop validation, reachability. If you learn a route internally in your network and the /32 goes away, you'll probably want to invalidate that route, which is pretty important, if you're advertising routes externally. And overall, when it comes to how many routes, generally most IGPs hopefully are pretty, skinny with regards to, just point-to-points and loopbacks and not really customer routes. The other part is that you want to split the rib from the fib. So we kind of highlighted that you need to separate the two because one's going to be way bigger than the other. In Juniper, luckily, there's one easy way to do this. I think XR has a similar way you can do it as well, but the whole idea is that you want to basically turn everything that you learn from BGP and push that into the rib of the router and not directly into the fib. And in the case of, what goes in which one? Well, obviously what you should be qualified for going in the fib should be, directly connected interfaces. Obviously the directly connected, you want to be able to forward it to it, the IGP routes, and then you can say, well, internal networks, things like that, and then a default route, really. So if you have traffic coming inbound, where are you going to send that traffic? And there's a few different thoughts on what you can do here. The problem, obviously, with a default route on a external-facing router, particularly if you're doing settlement-free peering, is somebody could simply just static route something to you and you'll carry it and forward the traffic. So it depends on do you trust your peers and a variety of other things, but that's really at the discretion of the operator. And so, in Junos, for example, you can write a simple policy to say what actually gets installed in the fib, and if it's BGP routes, you can match on community. So it's a pretty nice granular ability to have. The other part is you need to obviously establish IBGP connectivity within your internal network. You need to learn routes, and it needs to go both ways, from peers back inside your own network. There's one thing that you can actually turn on in Junos today, which is BGP add paths, which is actually a pretty cool feature. So you can learn the same prefix from multiple external pairs, and you can advertise each valid path back inside your network. Traditionally, BGP is only going to select one and send it back. Now you can open the doors and really give that kind of granular routing control and giving other routers in your network a good view. So add paths is something really cool. There's no such thing as a free lunch, so it's going to obviously have a higher memory footprint because you're learning that route X amount of times in BGP. So you have controls around that, and I think right now in Junos you actually can put a policy in front of it to say what routes are actually qualifiable to put into add paths. So you can actually declare which prefixes you want and which prefixes you don't want to advertise add paths for, and how many n amount of paths you want to install. And kind of getting to what this is all about is really next hop tricks, because the whole idea is, we're getting something for nothing. We're not filling up the fib on these tiny little boxes. What are we doing? Well, it's back to the BGP unicast label. In this case, we're using MPLS with a unicast label to make this work. And to make this happen, you basically need to take all your peering interfaces and you need to advertise their point-to-point into IBGP with unicast label. So basically, you have a peering router, you want to get the point-to-point interfaces so that they have an MPLS label associated with each individual peer. So you have peer A over here, well then there's one MPLS label going to that particular router, another peer, there's another unique label. And the way to do that, it's kind of interesting. You could think, okay, well I'll just redistribute connected in BGP, but it doesn't work that way. All it does is it advertises an implicit null label, which doesn't help you because that just tells the router to pop it and then it gets processed for an IP lookup. So that doesn't help you. What you actually have to do, and I was just playing around with it and it worked, which is that you have to advertise a unique 32 of the remote end of, let's say, a /30 into BGP. I thought, well, how do you do that? I mean, you can redistribute connected, that's not doing it. Well, if you redistribute static, how would you do that? And actually, if you static route the peer's remote end with the next hop of itself, its own IP address, that apparently does the trick. And it'll advertise a unique label for each individual peer destination address. The other part here is with next hop tricks. If you're advertising all this internally and you're learning routes from peers, you want to advertise the true next hop, which is that it's coming from the peer interface. You don't want to rewrite next hop self because that just tells packets to go to your router and then it gets looked up for IP processing at that point. You want to advertise the true remote end, which is the actual peer BGP neighbor address. And by doing this, you basically bypass the IP lookup on the pairing router. So you don't need to have all those routes in the fib because it's basically coming in on a label and then going out, IP datagram. Now, here's some graphical examples of what it all kind of looks like. In this case, here's our little cheap pairing router. It's got different links, individual 31s, because 31s are cool. And you have different colors here. And in the rib, you have, let's say, each peer is advertising you individual /24. And then in our fib, we have labels that are allocated, which just happen to match up with ASNs that I've worked for, and the individual /31s as well. So your router locally knows, oh, anything that comes in label 7132 goes out, 001. Anything that comes in 7018 goes out this one, and 4436 goes out the other one. As well as the individual /31s are known within the fib because they're directly connected. And then what happens is you take those routes that you have that you're learning through BGP and you advertise it, let's say you have a route reflector infrastructure, you advertise, the IPv4 unicast address family in this case, so the internet route itself, and then you advertise the unicast label, which is basically the corresponds to the prefix and the label associated with that pair. And then somewhere farther down in your network on a router that can have a full fib, it's basically looking in the fib and says, oh, for this /24, I see, via add paths, 3 paths to get there, and their next hops resolve to these routes that I see to go through the actual interfaces. So for 10.0.0.0/24, the next hop is 10.0.1.1, which corresponds to label 7132. So what that kind of looks like is basically, here's your router somewhere deep in your network that wants to push traffic out to the internet. It's going to send an MPLS outer label, which will carry you all the way to your, cheap peering router. It pops it, it gets the inner label, and the inner label basically strips off the label and then forwards the datagram out. So you basically eliminated the need to have the entire big routing table on that little cheap box. So what does that look like? If you look on the actual peering router itself, you basically have this corresponding, this label over here goes to this interface, this label over here goes to another interface. So it's fairly simple in terms of what actually goes into the fib. And if you try to trace route, you see that they'll go through different paths in the network, and you can actually see the label stack as it goes through. So it has the outer label just to get you through the network to your peering router, and then it has a local label that actually punts it out to whichever individual peering interface you want. So that's great, and now you have this really limited fib router, and it's doing all this outbound traffic, but you still have traffic coming into your network. So what do you do about this? And this really depends on the kind of network you are, how many prefixes you have internally. So if your internal routes of whatever you need to route internally within your network is larger than your fib, that's where you kind of have to cheat. And by cheating, I mean you're going to have to point a default to basically tell your router that, hey, for all this inbound traffic, you need to go to something that has a full table because I just don't have it. So let's say if you just deploy this in a model where you have your cheap pairing router hanging off a core box that has a, not unconstrained fib, you could just punt that traffic up. Or there's some other tricks you could do. You could just basically say, oh, that default route it to this other router that may be adjacent or somewhere nearby that does have a full table. And it really depends on your network and, can you afford to have that traffic possibly loop through, another router in your network? Depending on some networks here, I mean, obviously the ratios are different. If you're heavy outbound, maybe this is a big problem to have some of that inbound traffic loop down through another router just to go through that lookup. But if your internal routes are few, you don't have that much prefixes inside, you could probably just throw that in the fib if you have enough room. And once again, the problem with doing that default is that you're really at risk for someone pointing static routes for you over an exchange and for other prefixes. And if you're not watching, obviously somebody could abuse that. So back to this whole experiment, and this sounds really great. Does it really work? Well, let's look at one Juniper running router here. It appears to work. I mean, show route table MPLS shows that it's popping out through the individual interfaces. Unfortunately, it doesn't. In this particular example that we were using, the EX4500, it seems to have all the mechanics to do MPLS, but it's not actually, as you can see on the Marvel chip, it's refusing to install it in there. And the MPLS doesn't appear to work, although it appears configurable and it's not officially supported, it doesn't seem to work. So what is this really all about? Well, basically you're almost there in terms of technology-wise and what you can buy to do something like what we're describing here. BGP add paths gives you the ability to have multiple BGP path visibility. That's really nice. The BGP, or the RIB and FIB separation really gets you to cheat and do what you can on the box. Basically put that big routing table right in the RIB and only put what you really need to have in the FIB, which would be labels and local routes. It is feasible. You can certainly do this today on a variety of platforms, although they're a bit more pricier. MX240, it works on some Cisco box as well. But obviously the whole point of this is doing this on the cheap. So really what's available there? Basically, there's hope, in particular on the EX models. I believe they do have MPLS coming at some point in time. There's other platforms, Broadcom and things like that, which I believe are probably at some point in the near future. At some point, they've got to basically have MPLS support to do this. I would imagine it's really just a matter of time. Don't initially expect any kind of great software implementations of MPLS. So, expecting a full RSVP LDP stack is probably asking for quite a bit. If they had that today, you could probably take the same box and make it, a simple LSR in your network and make it a core box, devoid of any kind of routing table. You may have to rely upon some really minimal implementation of MPLS, where you may have to rely on static or nailed up LSPs. Routing protocol functionality on some of these boxes aren't completely there yet. They may only be shipping with OSPF, and BGP and ISIS is just not there. In this case, we use the example of Juniper EX because it does have a lot of the routing capability of Junos right there running on some of the commodity platforms. So it's there. We used it for example. It mostly works except for the whole MPLS part. And then there's still kind of a question of, okay, all this merchant silicon, can it even do MPLS and some of the things we're asking? I mean, push pops and swaps, can it even do that? Is performance going to be really bad? It's certainly questionable when I think we start to see some of this stuff come out in the next year or so. So that's pretty much about it. So I don't know if there's any questions.
Are there any questions? The mics are open. I've got a question that somebody sent me over IM. It's from Nick that works at the INEX. It's talking about a lot of the smaller boxes. They've got quite shallow buffers, and have you any thoughts or insight in how the network's going to behave in situations where you've got like pretty hot links with these shallow buffers?
That's definitely an issue. I mean, you see a lot of these boxes, they do have small buffers, and that doesn't make it very conducive, I think, in certainly certain internet environments. And I think the only thing you can do there is really you either operate in that manner and deal with the performance as it is, or hopefully they add additional buffers at that time. But that can certainly be a showstopper.
Joel Yegley. Thanks for this work. I've been sort of kicking this idea around with our EX series boxes for a while, and I'm sort of eagerly awaiting the feature enhancement that's supposed to be coming for those. But I think this is really useful work, and it points a way towards using boxes that don't actually cost like $15,000 or $20,000 per port. Yeah. To do this, and in the context of buffers, I mean, one of the biggest problems that I see with the buffers in these platforms is draining stuff from one 10 gig port through a bunch of 1 gig ports, and when the edge is like mostly congruent, that seems to actually work a lot better. Thanks.
Yeah, and I'm really excited about. I think what's probably in the next year coming out is you see a lot more MPLS features coming in the data center. I think it's going to drive a lot of these cheaper boxes to support it, and that's really the missing piece. Once you add the rounded name, and the software isn't all that great on top of it, but once you get it all together, I think it opens the doors to do a lot of cool things. So.
Okay, if there are no other questions, thanks very much, Tom.